Okay, so this is sinh t and cos t. I hope this is correct. Let me see. Yeah, minus sinh t cos t. Then we change t to tau because t can be anything. Okay, t in this case can be. So we have an example here. Yeah, t can be tau 1 or tau 2 or tau 3 or tau 4. Any value is okay. Okay, so this is tau 1, tau, we call tau. Okay, so at time t equal tau, this some point in material coordinate x1 and x2 go to this point, x2, this point. This is 0, 1 point, and we also call x star. So some point after time tau, this will come, this go to this point, right? So if there is another point, maybe after tau 2, this go to the same point. So we use tau instead of t. And tau can be anything. Tau can be go from minus infinity to plus infinity. Okay, so in other words, this is the position. Okay, we have this two. This is the point. This is this point. This point, right? Then after tau, this go to 0. Yeah. Then we want to know this 2 point. What is the where is this point or particle at t equal 1? This is what we want to know. At t equal 1, this will be some point in spatial coordinate, this point, right? So to obtain this point, we use this equation, this top equation, right? So here to make this small, so we put this minus sinh tau to x1 minus sinh tau to x1, right? Then we put cos tau to x2, cos tau to x2, yeah? So this goes like minus sinh tau cos tau sinh t minus sinh tau cos t. Yeah, and there is a formula, right? Which I don't remember. I don't quite remember. There is a formula. Okay, let me just believe this textbook. So we have a formula like this. Cos t sinh tau plus sinh t cos tau is sinh t minus tau. Okay, cos t cos tau minus sinh t sinh tau equal cos t minus tau. So this is the spatial point position in spatial coordinate at some t. No. So this point, this material particle moved to this point, no, after t. This point, this point is original point, so t equals 0. So this particle at t equals 0 move to this new point, which is given by this and this. But in this particular case, we need the streak line when t equals 1. So we put 1 here, 1. Okay, but then we want to eliminate tau. So if we eliminate tau, we obtained this curve. And this is just the same as before. Did we draw this one? This is more like this one, I think. You can draw this curve x1, x2. There is there is this point, right? This point and this point. And I think this goes like this. So eventually this will move, approach this. Yeah? Of course, for steady flow, given by equation 624, all three lines are identical. Why, of course? I don't understand why they say of course. He said of course. This example illustrates the procedure involved in finding these lines from the given motion. I'm not sure why he said of course. I would say this is a coincidence. Just a coincidence, accidentally saying. I'm not sure why he says hyperbole. I think we have to be careful, we have to drop one hyperbola out. We have to examine the condition, original condition, if lower hyperbola is also satisfy the condition or not. So anyway, so we go to next part, which is the length, volume, and area elements. In this section, we are interested in finding the material derivatives of elements of arc area, arc length, area, and volume. With xi equal xi of particle large X, we begin by computing. We begin by computing this. Interesting, right? So this one, this is a partial xi, partial large X alpha. And then only this is a time dependent. Only this is time dependent. So this we obtain partial Vi, partial X alpha, right? Then we have this JJ summation, JJ summation, right? So we change partial Vi, partial small xj, then we have to do partial small xj, partial large alpha, large X alpha, using a small xj as intermediate parameter, right? So then, removing partial alpha, we find, how can we remove it? How do we remove it? Okay, let me stop it now.